Hello, we are the ABC Fastener Corrosion Screening Team with team members Isabelle, Kendal, Sophie, and Luke. Our project goal is to develop an accelerated corrosion screening test for fasteners using electrochemical impedance spectroscopy. This is our project overview. It starts with screws, some of which are put through long-term corrosion tests by our sponsor, which we use for failure analysis, and others that we use for our own EIS testing.
We were also given samples that had been corrosion tested in either a salt spray chamber or driven into treated lumber. These two test methods are used because the salt electrolyte mimics a coastal environment, while the lumber tests mimic more general use. It is the copper in treated lumber that is known to accelerate the corrosion of steel fasteners, while salt can increase corrosion due to the increased conductivity associated with more salt. Both of these tests rely on visual evidence of rust to judge performance, but it can take a long time for rust to become visible, especially as coatings improve with time. As you can imagine, waiting several months for results is not ideal, which is why a screening test may be useful. Electrochemical impedance spectroscopy observes electrical behavior by measuring a current response to some potential at different frequencies. The current response changes as the coating breaks down, corresponding to a loss of protection. Then impedance calculations tie in the potential and current in a way that is similar to resistance.
This is our hypothesis for this project. It was, if EIS is performed on coated fasteners, then the fasteners will rank similarly to how they did in the long-term corrosion chamber, because corrosion is an electrochemical process and an EIS measurement can quickly measure changes to a coating's electrochemical signal while it is exposed to an electrolyte. And then this is our overall DOE that we use to assess the most important factors among coating, driving, solution, and time. And then this, transitioning to our failure analysis portion, this is a top-down view of one of our mounts showing the heads of each fastener. These samples were used to analyze how driving into treated lumber affects their performance, as well as to assess the corrosion mechanism. We determined that the corrosion mechanism was crevice corrosion, and this is an example of a fastener that was driven into treated lumber and underwent a long-term corrosion test. The driving created crevices of damage at the midpoints, which are circled on the slide, and they were ideal environments for corrosion.
Following this, we looked at our EIS data, which we separated by coating, so we could have direct comparisons to rank them to each other. The first way we did this was by looking at the EIS area under the plots that we got, and the highest performance coating had the smallest difference in area, while the lowest performance coating had the greatest difference in area. So looking at our data specifically for salt testing, the 74% decrease in area corresponded to our electrogalvanized zinc sample, whereas the 66% area corresponded to our zinc dip spin sample, and the 96% decrease in area corresponded to our black top coat sample, which means that this sample performed the worst. So ranking the three coatings, we had the zinc dip spin coating performing the best with the smallest area, followed by electrogalvanized zinc, and our black top coat performing the worst. And when comparing this to ABC's rankings, we see that the rankings are the same, which is a good sign for our testing. So in conclusion, our hypothesis passed because our rankings were the same, so our EIS shows promising results for using accelerated corrosion tests in industry, which brings our testing time down from a few months to a few hours. Thank you for listening to our presentation.